All right, very good. The title of this talk is Reactive Java EE, Let Me Count the Ways. Let me start by introducing sort of the genesis of how I went about creating this talk. It's sort of got an interesting story behind it. So a few years ago, I guess a couple of years ago, and to be precise, I was talking at a Scandinavian conference called Oradev. And I was delivering yet another Java EE talk. And at the end of the talk, there's this gentleman that came up to me and said, hey, have you heard about this thing called reactive programming? And it was relatively new back then. So I said, yes, of course, it's that thing that the Scala Akka guys keep talking about. It's the hipster thing. The next thing that he told me actually somewhat shocked and surprised me pleasantly. So what he said was, I don't think so. Because I really believe that I am writing a reactive application with really nothing much more than vanilla Java EE APIs and a little bit of Java SE. So I was very intrigued with this statement because I didn't know quite whether to believe him or not. So I said, okay, that's interesting. Let's have a chat. So we went to Malmö, Sweden, which is where this conference is, and we had a chat over coffee. And he sort of explained what his thinking process is with regards to this statement. Actually, I was surprised to learn that I actually had something to learn from this gentleman because he is actually quite right. So that is the genesis of this talk, and in the end, this is what this is the message that I'm trying to deliver to you at this moment, is that believe it or not, you can actually write very, very reactive applications using nothing much more than vanilla Java EE and a little bit of Java SE. And in fact, we can do better than the gentleman. So the gentleman was using Java EE6. Now that we're using Java EE7, we actually have more things to add to the catalog in terms of our arsenal in deploying reactive solutions in Java EE applications. So this is basically what this talk is about. It's a bit about an introduction of reactive programming. And this is surprisingly difficult. We'll talk about why this is and sort of how we can arrive at a sensible conclusion without going nuts. And then we'll be doing a pretty fast tour of sort of the reactive features in Java EE, and there happens to be quite a few of them. In fact, in the 45-minute time slot that I have, I won't be able to cover all of them. I will tell you the things that I'm going to skip. However, in my extended slide deck, which I'll show you how to get to that, I actually do cover pretty much all of the reactive features that are in Java EE at the moment, as well as the features that we could potentially talk about in the future, Java EE 8 and beyond. And believe it or not, Java SE8 has something to do with this as well. Java SE8 introduced quite a few features that are very, very helpful and very, very powerful when combined with the features that you already have in the Java EE platform to write reactive applications. All right, so a little bit of a background and a little bit of an agenda. Now let's get to more complicated matters. So what precisely is this thing called reactive programming? And it is surprisingly difficult to define. Okay? In fact, I would say the best you can hope to do is define it for a given context. It's almost impossible to come up with a universal definition of reactive programming that applies everywhere. I know this is as confusing as it can be. But at least for the purposes of this talk, we can arrive at a relatively simple, streamlined definition. In fact, I would argue, I don't want to impose this on somebody else, but I do want to argue that the simple definition that we can arrive at actually is fairly universal. You can apply the same definition in different contexts more than any other definition that I've come across for reactive programming. So how did I arrive at this definition? That's an important thing to understand. What I did was that I took two different pathways and met halfway. How did I do that? So the first pathway I took is a historical perspective of precisely what is the etymology, the history of this term in the technology dictionary, reactive programming, or rather, more specifically, simply reactive. The other road that I took is to try to decipher what exactly are we trying to achieve rather than trying to define what it is, what exactly is it supposed to be doing? And as it so happens, I think in the end, I intersected, okay, those two paths intersected fairly nicely. So historically speaking, what precisely is reactive programming? The first time this term properly entered the technology dictionary is actually somewhere around the late 80s. And the original definition is simply put, a part of an application that changes, okay, reacts to a change elsewhere. Okay, so you have point A in your application, point B in your application, and somehow point A affects a change because point B, something changed in point B. A classical example of this is an Excel spreadsheet with a formula in it. Okay, so when you have a formula, the formula will be dependent upon several other cells, correct? So when the value of those cells that you have in your formula change, okay, the value in the cell with the formula will also change. Right? So this is the classical definition of reactive. In the end, what this means is a few warm and fuzzy things like asynchronous offline processing, or events, or message-driven programming. So believe it or not, we'll talk about what we are trying to accomplish with reactive programming in the end, but these are essentially the core principles of what makes something reactive. Okay? In particular, I'd say the following things. Okay? So largely, when you are doing reactive programming, these are the kind of things that you'll be thinking about. First and foremost, event-driven systems and message-driven systems. So the example of my Excel spreadsheet applies. Right? So you get an event, okay, some kind of notification or some kind of state change, and then you have to react, okay, somewhere else in your system based on that event or based on that message. Similarly, another common thread in reactive programming concepts is asynchronous programming. What does this mean? Simply put, this is processing something outside of the current thread. Okay, so you have a current processing thread, and you're going to do something else on another thread instead. And lastly, another important concept that's very common to the reactive nomenclature is non-blocking. What does this mean? What this means is that you make an attempt to not block your current thread in some way or the other. In all reality, the problem is, the reality is you cannot write a completely non-blocking application. No matter what anybody tells you, it's an impossible problem. What you can attempt to do is reduce the possibility of blocking. Okay? So this, again, is an important fundamental concept. These three things taken together, the more of these you're dealing with, likely chances are you are dealing with reactive programming. In fact, these three things fit quite nicely in the context of Java EE. But beyond that, let's move away from the simple definition a little bit just for purposes of thought experiment. So what are the other things that are sort of put on top of these basic concepts? Okay, and frankly, to be honest, I think this has something to do with marketing rather than intellectual honesty. But with regards to reactive programming, you'll see other terms like responsive. The reason I don't count responsive as in my core definition is because I actually believe that responsive programming is an effect, is a goal of reactive programming, not a fundamental aspect. Similarly, you'll hear concepts like resilience or fault tolerance. What does this mean? What this means is that if you have a hardware failure or a catastrophic software failure somewhere in your system, the system should be robust enough to self-heal. Okay? And things like is elastic or adaptive. And what this really means is that expanding and contracting the number of available resources based on current requests. Okay? And this can take many forms. It can take a form of physical machines being allocated and deallocated. It could simply be a matter of deallocating and deallocating threads on a thread pool, connections on a connection pool, and the like. And finally, scalability. What does this mean? What this means is simply handling high load gracefully. Right? So if you have a sudden high load, you simply don't crash and reach a system halt state. You can somehow move forward and achieve some kind of throughput. Now, you might think, okay, responsive, I said, is a goal of reactive programming, so let's not count that in the basic definition. What about these other things? Are they not important? Clearly, they are. However, the key thing to understand here is that in all reality, whether or not you're dealing with those fundamental concepts of event-driven programming, asynchronous programming, and NIO or not, okay, even if you are writing a highly blocking CRUD-based API, in any kind of enterprise system, these are still going to be concerns for you. Okay, they have remained concerns for us for a long time. In fact, these concerns are so important that in the Java EE platform, we actually do this at the runtime level. You don't even look at these things at the API level. Okay, the runtime handles all of these concerns for you. So what am I trying to get at? So what I'm trying to get at is twofold. These concerns are not specific to reactive programming, so it doesn't make any sense to include these in the definition. Number two, in a Java EE case, it really doesn't make any sense because Java EE doesn't handle these things at the API level. We've long learned to deal with these things at the runtime level instead. So this really should bring us back to a very simplistic definition of what reactive programming actually is. Now, to get our heads around this a bit more, the next thing we should try and think about is what is it that we are after? Okay, and it so happens that the things that we are after with reactive programming have been with us for a very, very long time. All right, what are these things? Well, first and foremost, that same old word again from the previous slide, responsive. Okay, responsive systems. What does this mean? What this means is that the system should make an attempt to appear as though it is reacting to user input, responsive to user input at all times. A classical example of this is sort of the Windows spinning little, what's we call it? Pardon me? Yeah, spinning circle, you're going to call it that. This is a spinning timer. Okay, so why is that? What's essentially is happening there is that you're getting user input. You happen to be doing some kind of long-running operation. So instead of simply blocking and halting the program and sort of freezing your entire application, and hence giving the user the impression that the system may or may not be responding to his or her input, what you're doing in that case is processing things on a background thread, doing asynchronous processing, one of the reactive programming principles, and appearing as though you are reacting to user input in a timely fashion. More importantly, another core goal we want to accomplish through these reactive programming paradigms is principally high throughput, okay, which means as much as you can process in a given amount of time, not necessarily as fast as possible, mind you, as much as possible over a period of time. And how do you do that? The way you do that is by not overloading yourself and making optimal use of hardware and software. Okay, meaning making full use of the available CPUs that you have, making full use of the available I/O resources that you have. Okay, so that's what that means. Again, this goes back to multi-threading, event-driven processing, and NIO. Finally, there's actually some class of systems that are inherently reactive. Okay, what this means is they're inherently event-driven. And I actually worked on such a system a few years ago, quite a few years ago, in fact. And I have to say, what we were developing, in fact, was a reactive system. So what was this? This was essentially a trading system. Okay, so trading systems actually don't have any UIs. What they do is that they take input in terms of stock exchange data. Okay, you make a trade, and that goes into this stock exchange backend as a message. All right, and the stock exchange engine actually calculates the state machine change. So what effect did this one trade have on the overall market? And then what it does is it simply produces event output to say, this is what occurred. Okay, and somebody else deals with that, perhaps a stock ticker application, or perhaps some trader looking at his very confusing and crazy looking screen and the like. All right. So the other question that should remain then is, if these things have indeed been with us for a little while, why are we now suddenly spending so much time looking at it now, and why is it suddenly a buzzword? frankly, I don't have a clear answer to this. Okay, some of it may simply be historical accident. It may be that a bunch of people have decided this is a cool new buzzword, and they want to get on board with it and use it as a marketing vehicle. However, maybe a more responsible view of this could be something like the following. There are two principal drivers that I see that are reasonable in why we need to think more about reactive programming than we used to in the past. One is that the nature of the internet is actually changing. How many people here have heard of the term IoT, Internet of Things? Excellent. Okay. So what's the basic problem here? The basic problem here is that we as human beings are biological systems. Biological systems are capable of complex processing, but not at a very fast rate. Okay? So what this means is that when we are interacting with a system, largely the nature of the internet today, we are actually not that fast. Right? So we do something on a screen, we have some think time, and then we do something else on the screen, and that's how it goes. On the other hand, when you're talking about device-to-device communication, devices don't have think time. Right? So what that means is their input and output, and their communication rate is both higher in frequency and higher in volume. Right? So what that means is the net throughput, okay, for all of those server machines that are on a device-to-device IoT system must be higher, okay, than it would be otherwise for human beings. Hence, you need to think about the reactive programming principles, making optimal use of resources, of hardware resources. Also, if you look at some analysts like Gartner and the like, what they will tell you is that we're entering a new era of globalization. What this means is that our systems today are by and large localized. Right? So our markets are local, perhaps at a national level or at a regional level or what have you. If you are suddenly indeed talking about moving from a regional or localized user base to a global user base, what does that mean? It means a net increase in the number of concurrent users. Okay? Again, thereby making it more necessary, okay, to make optimal use of hardware, and hence, again, making reactive programming a bit more relevant than it has been in the past. All right? Don't take this for granted. This is simply me trying to explain why this sudden trend. But regardless, this has been a valuable technique and something that you should know about, okay, should you run into this situation. Be cautious, though, that I really believe that this thing, reactive programming, is not very popular. It hasn't been very popular for a long time for a reason. Okay? The principal reason is that reactive programming, all of these concepts, are harder in nature. No matter what you do, no matter how much syntactical sugar you throw at the problem, the reality is that synchronous blocking code is a lot easier to write than asynchronous non-blocking code. Why is this? This has to do fundamentally, this has to do with the way programming languages have evolved as a response to, again, human nature. We, human beings, are in fact parallel processing machines. Okay, so as I am standing here, my body is actually performing several parallel operations. I'm breathing, my heart is pumping, there's blood circulating through my veins and the like. But the reality, though, is that my perception of the world, the way I interact with the world, is by and large serial. Okay, so I am not perceiving my world or my functions to be parallel. I am perceiving them to be serial. And that is why, even psychologically thinking, the synchronous blocking code is a lot easier to deal with. It's easier to comprehend than the other way around. The other thing you should understand is that hardware is always the answer. At the end of the day, okay, what you are trying to do with this, majority of the time, with this reactive programming principles, is optimizing hardware. Well, guess what? Hardware these days is cheap. Okay? So one way of achieving scalability is simply throwing hardware at the problem. And what that will accomplish is to avoid having a more complex system. Right? So these are all things that you should weigh carefully before you enter into the realm of reactive programming wholesale. All right. Any questions on any of this? All right, moving forward. Okay, so what is it that Java EE offers in terms of reactive programming? Java EE actually offers quite a bit. Some of this is exists because of unconscious decisions that were made over a period of time, because we deal with an we're talking about an enterprise system, okay, and these are concepts that have been around for a long while under a new term these days, but have been around for a long while. That's why we've had these concepts in the platform for a long time as well, okay. And of course, these days we are more conscious about this. Okay, we're thinking more along these lines and adding more and more of these features. In fact, what you will find out is that we actually have these sorts of features, reactive features, in every layer of the Java EE APIs. Okay, in all layers. What this means, though, for you, is that you can go whole hog and write an entirely reactive system, and you know, from the UI layer all the way to the database layer, you can have an entirely reactive system. Okay, or you can also pick and choose. Okay, to make a certain part of your application where it makes sense reactive, whereas most of the rest of your system may still be synchronous blocking code. All right, so. Here's a brief catalog of what Java EE offers today in terms of reactive programming concepts. Again, I told you I won't be covering all of this simply because I can't in 45 minutes. So these are the things. Okay, first of all, JMS. We'll talk about that in a second. EJB3 offers a few reactive features, namely message-driven beans and asynchronous session beans. We'll talk about that in a second. CDI, another technology at the Java EE component layer, also offers reactive features in terms of CDI events and observers. I actually won't be covering these, but they are in my extended slide deck that you can download later. Similarly, in the protocol layer, we have asynchronous programming and NIO support in servlets. We have asynchronous processing in JAX-RS, both on the client and the server side. We don't have NIO in JAX-RS yet, but that is happening. Okay, that is happening in Java EE 8. The WebSocket is an interesting case because it is inherently actually designed for non-blocking code. However, even there is additional asynchronous processing support. Again, I won't be covering that. WebSocket today, again, it's on my extended slide deck. And finally, there's this brand new API that was added in Java EE 7. It's called the Concurrency Utilities for Java EE. This is, if you can call it, basically the poster child for asynchronous programming in Java EE. Definitely something you need to look at if you're looking at creating reactive systems. Okay. So let's start at the oldest and perhaps the most significant reactive API that we have in Java EE, and that is nothing much more than JMS. Okay, JMS at heart is designed for message-driven and event-driven code. Okay, it is designed for essentially processing these messages and events in an asynchronous fashion. However, more than that, it does so in a loosely coupled, highly reliable, transactional, durable, fault-tolerant, error-tolerant, and clustered way. Okay, this is the backbone of what you can. This would form the backbone of any reactive system that you would create in Java EE because of these characteristics. It doesn't get more robust than this. Okay, if you are talking about doing event-driven code, asynchronous code in a reliable, well-determined fashion. Okay, you'll be hard pressed to come up with a better programming model that balances simplicity with power. Okay, and we'll see that in a second. Similarly, there's another powerful construct that has been in the platform for a very long time called message-driven beans, and this is nothing but a highly declarative, very, very simple, but very, very powerful way of receiving messages in Java EE applications. Again, it gives you a whole bunch of things other than the simple act of receiving a message. It's, again, transactional, thread safe, pooled, reliable, load balanced, fault tolerant, error tolerant. You cannot get more powerful than this without introducing additional API complexity features. All right. If you haven't, so let's start from the simple end, sending an event, okay, in Java EE applications using JMS. If you haven't seen JMS before, this is how JMS 2.0 looks like. Very, very powerful, very, very compact API. Take a look at this code for a second. What I'm doing here is that I'm taking an object that I have, handling event registration attempt, and then I'm using it as a message. I'm sending this message payload, in this case, to a queue. All right? And take a look at how powerful this is in Java EE. It's just a one-liner. All right? And in this one-liner, I'm doing quite a bit. It uses a Fluent API pattern. I'm setting a bunch of quality of service parameters, and I'm also setting some filter values as well. So I'm setting a property called source and setting it to some source value that I have. So a whole bunch of stuff going on here. Okay, again, it doesn't get more compact and more powerful than this. And there's more going on behind the scenes. Okay, this message delivery, although we are not seeing it here, is also using acknowledgement and is also using transactions behind the scenes. All right, all without you having to do very much at all. Similar story on the message-driven bean end. Okay, this is how you receive the message that we sent out. Again, a whole bunch of powerful stuff going on. Auto acknowledgement going on. Transaction management going on. Pooling going on. Thread safety going on. Error retries going on behind the scenes. Okay, and all you're really doing is specifying a few bits of metadata. Okay, what message am I listening on? And in this case, using the selector. Okay, this is again another powerful mechanism to do event filtering, if you so wish, in Java EE applications. And this is, believe it or not, even just the beginning. Okay, if you look at JMS 2.1, we are both simplifying this API even further and actually adding more power to it. Okay. The second important construct, and very simple construct, again, for doing reactive type programming, more specifically asynchronous processing in Java EE, is asynchronous session beans. Okay, again, you'll be very hard pressed to find a construct that is so simple with so much power behind it. It's just a POJO with an annotation on it, and you still get things like transactionality, you still get things like thread safety, you still get things like pooling. What you don't get, which you get in case of JMS, is that this is no longer loosely coupled, because at the end, what you're trying to accomplish here is simply throughput, okay, not necessarily loose coupling. You don't get persistence, you don't get fault tolerance, and you don't get error tolerance. Okay, but it is very, very simple. I'll show you how. Right? It's as simple as that. Okay, if you want to spawn another thread to make to give yourself a bit more throughput, it's simply a matter of throwing the @asynchronous annotation on a POJO method. That's it. That's all you got to do. Okay, it's almost ridiculously simple. But let's assume for a second that you're doing something a bit more powerful. Right? So let's assume for a second that you actually do care about your output. You don't simply want to do a fire and forget type thread spawn. In this case, let's say we have a long-running report that you want to generate. Even in this case, things are going to be relatively simple. See, the only difference, this code, although it is still doing asynchronous programming, actually still looks very, very synchronous. The only big differences are you are returning, instead of returning the report object, you are returning a handle to a Java util future, okay, that you're going to handle in your client code. And as a parameter to that, you're giving it the actual payload. The other big difference is that instead of returning the actual return type, okay, you're simply wrapping the return type in a utility object called async result. But other than this, you're looking at this code, it's very, very synchronous. It's synchronous blocking code. Yet it is completely asynchronous. Okay, this entire report generation actually happens on a separate thread from the invoking thread. All right. Interesting problem that we will revisit later is this issue of Java util future. Okay, I'll give you a hint for the latter part of the presentation. Moving more into the protocol layer, servlets have both asynchronous processing as well as NIO capabilities built into them. And in fact, it doesn't stop there. In Servlet 4.0, we're also thinking of introducing yet another reactive concept called Reactive Streams. I won't talk about that too much, just because we really don't have time to deal with that. But that's another way that servlets can be more reactive. Long and short of it, it's basically a way of handling load. Okay, so if you have a load imbalance between the client and the server, this is a way where the Reactive Streams is a way where the client and the server can sort of negotiate, okay, what rate that they can collectively handle to maximize throughput. Okay. Now, let's explore how asynchronous servlets look like. right? So let's revisit our example from before. Generating a long-running report. In this case, the report is being triggered by accessing a URL called reports. Okay, it's you're issuing a GET request to this URL, and you're expecting to generate a report. The first thing you'll notice is that the semantics of the asynchronous servlet. An asynchronous servlet must explicitly be marked by async supported equals true. I'll explain in a second why this is. Okay, but it'll be relatively simple to understand why. The next thing we're doing here is that we're creating this object called async context. Okay, and we're creating it from the HTTP request. Again, I'll explain in a second why this is. But let's move on to the core of the asynchronous nature of this processing. So how we are actually starting an asynchronous, how we're actually processing the report generation asynchronously is by spawning a new thread. Okay, that's what the async context.start method is doing. It happens to be a convenience method that is in async context. What this does is that it takes this in a runnable object and spawns a managed thread behind the scenes, okay, and gives that work to that managed thread. Hopefully, by now, you're all familiar with this funky syntax. Okay, yes, what is it? Lambda expression, yes, okay. So this is very important, okay? This is an important point to make here as well. I won't go into too much details talking about lambdas, but notice syntactically what the net effect of this code is, okay? It is having the net effect of the lambda expressions in this case is that it makes asynchronous code look synchronous in nature. Okay, it just looks like, oh, there's a bit of synchronous code here. I'm just taking this block of code and saying, you know, execute this part asynchronously. But the net effect really is that this will actually execute on a separate thread. So what this means now, okay, is when you invoke thread.start, sorry, async context.start, the doGet method will return immediately. Okay. Think about this for a second. In a normal servlet, a servlet request, as soon as you return from the doGet method, the actual connection, okay, the inbound connection for the request is actually closed immediately. All right. If we did that, would we be able to do anything useful? No. All right, because by the time we're actually ready to produce output, we would have already lost our connection. All right, and that is why you need the async supported equals true flag. What this does is that it tells the servlet container for this particular servlet, do not, okay, return the thread to the, do not close the connection when this thread, request thread is returned back to the pool. Okay, even when this doGet method returns, hold on to the connection. Do not close it. All right. And how do you get a handle back to that connection that is likely passivated into disk? Well, you have a handle to the async context object. Okay, and that is in fact what you're doing in the end. You're getting the report parameters not directly from the HTTP request because you don't have a direct handle to it anymore. You have to get a handle back to it from the async context, okay? And similarly, when you print the report, you need to get your output stream from the async context. And finally, when you are all said and done, you call async context.complete, okay? And when you invoke async context.complete, basically what happens is that connection behind the scenes is then closed up. All right? So what is happening here? We are basically, what we are doing is we're quickly returning the limited resource, okay, an HTTP request thread back to the pool as quickly as we can, and making use of a longer running background thread to maximize throughput. All right. Now, how do you think this print report method is written? What's a naive implementation? What would you do? You're printing the report. How would you do it? Pardon? Session attribute, not quite. Okay, so you would a naive implementation would be HTTP request.get output stream and then print the report, right? So write a series of print statements to print the report, which would be fine in most cases. Okay, but think about the case for a second where your output is not merely a few megabytes. but let's say 100 megabytes or or a couple of, or maybe a couple of gigabytes of data that you're producing in this report. Let's say it's a large PDF file. You're producing this large PDF file over possibly a global network. Okay, so what this means is that in some cases you will wind up with blocking I/O. Right, your I/O will block on the print statement that you make because of network latency. All right. In the end, the net result will be that you are still blocking, still misusing your hardware, still misusing threads because now you have a blocked thread, even though it's in the background as opposed to an HTTP thread. So how do you solve this? Well, you don't write a naive print report method. Okay. In this case, the print report method will actually be using in I/O. Okay, to write the report as opposed to simply doing a simple getOutputStream.print. How do you do that? Well, this is how you do it. Okay, so you get the output stream as you always would, and then instead of writing print, what you will do is you will set a write listener on this. Okay, you will create a write listener and set the write listener on it, and lo and behold, this method is now returning. Okay, so this background thread is now actually done. All right. So question is, then how do you go about writing the response? The answer comes in the callback methods in the write listener interface. We'll see that in a second. Let's just go through this real quick. So I need 3 separate things: the output, the input, and the async context. Okay, in the constructor, I'm just getting a handle to those, and I'm creating the constructor right here. Simple stuff. More interesting stuff is here. All right. So there's 2 different callbacks on the write listener. One is on write possible, and the other is on error. On error is not terribly interesting. All this does is that it says, while I'm trying to write, if I encounter an error, please give me the handle to the error message, and when I receive that, I simply call context.complete, which closes up the connection. All right. More interesting is the on write possible method. So this is in I/O in action. Okay. In this case, what is happening is that we have a hook, okay, to the underlying I/O channel. The I/O channel will tell us when it is ready to write. All right? So whenever the I/O channel is ready, it will call on write possible to tell me, hey, you can start writing now. I'm ready to be written to. The next thing you will do is that you will not write all at once. Okay? What you will need to do in an I/O-based system is write in an incremental fashion. In this case, what I'm doing is I'm writing 256 bytes at a time. All right? So if you look at my while loop, all I'm doing is I'm keeping on writing, okay, in 256 loops. But there's also this interesting check, output.isReady. What does that mean? What this means is that upon each write, I still have to check whether I can do the next write call or not. Okay? If I cannot, I simply terminate this loop. Okay? And I exit the on write possible callback, and I wait for the next callback. Okay? And the I/O channel will then tell me again, hey, now I'm ready again, start writing again. And finally, you'll be done when you have nothing more to write. Okay? In bytes of 256 chunks. All right. Similarly, JAX-RS as well has asynchronous capabilities built into it. Syntactically, it looks very similar to servlets. Okay? In fact, it's just a little bit nicer capability than servlets. Similarly, there's also asynchronous capabilities on the client side as well. Okay? As I mentioned, in JAX-RS, there is no NIO capabilities yet, but hopefully we'll be building that in Java EE 8. In fact, that is part of the charter for JAX-RS 2.1, the next revision of the JAX-RS specification. All right, so how does it look like? Again, syntactically very similar to servlets. Basically, the async context version in this case is async response. Okay, instead of creating it manually, you simply inject it into your callback method. It is automatically suspended for you. You do whatever you need to. What's really happening is when I invoke the generate report method, because it's EJB async, it is actually spawning a separate thread. All right, and in that separate thread, I have a handle to the async response. I'm doing the async report generation, and then when I'm done, I'm closing off the connection. All right. Similar thing on the client side as well. All right, on the client-side API, the client-side API in JAX-RS is builder-based. All right, so if you want to convert something from synchronous programming to asynchronous programming, all you really need to do is add that async call, .async. All right, and there's two different ways you can handle handle async. You can either do it by future, good old future. Okay, we all hopefully know how to handle that. Or you can use callbacks instead. And we'll talk about these two things. These two things have slightly different trade-offs, but actually none of them are as good as another construct that was introduced in Java SE 8 called Computable Futures. All right. Moving forward, I'm going to skip over Java EE concurrency utilities a little bit. What is this? Okay, so simple explanation of this is, it is a way of safely executing threads in a Java EE environment. Okay, so in a Java EE environment, for various good reasons, you are not recommended to start a native Java SE thread. So new thread.start, don't do that. Instead, what you do is you get a handle to a managed executor service, okay, that is configured for you behind the scenes. There is one default one created for you. The default one is geared towards basically background processing, long-running background processing. And then instead of invoking your own thread, what you do is you call an executor and give it a runnable argument or what have you. Okay, whoops. Uh-oh, this is not good. Okay, going back to where I was. All right, that's as simple as that. It's actually more powerful than that. Okay, so the other important thing that this allows you to do is that you can create your own custom executor services, and you can tell it things like, for this particular workload, please make sure that it has so many threads on it. This is supposed to be long running or short running and the like. So there's a bunch of things you can configure on this beyond simply being able to execute a thread in a safe fashion. All right, moving on. There is actually a problem, a serious flaw, with both good old futures and callbacks as well. We'll explore that in just a second. To overcome these flaws, Java SE 8 actually introduces a brand new API called Computable Future. And the big difference is that this is a very, very reactive API. Okay, it is non-blocking in nature. It is event-driven, and it is composable and functional. Okay, we'll see why that is when we take a look at an example. In fact, with Java EE 8 and beyond, we'll actually be replacing every place where we're using future today. Okay, we'll replace it with the computable future. It is that good. Okay, and you'll see why in a second. So to understand why, let's explore this relatively simplistic looking code. It looks fairly harmless. Okay, what is it doing? It's underwriting somebody's insurance coverage. In order to do that, we're getting their assets, getting their liabilities, calculating a credit score based on their assets and liabilities, getting their health history, and calculating a health score based on their health history. Okay. This code is actually hugely problematic because it is almost certain to become a bottleneck in your system. Why is that? It takes time, but everything takes time. But what's the bigger problem? Each of these are potentially long-running operations that are executed in sequence. Okay, so that means that you're doing one lengthy operation and then waiting for another one and waiting for another one and waiting for another one. However, the reality is that these things can be written better by throwing more hardware at it, essentially doing each of these operations on their own separate thread. Okay, that's how you can get away from this, or try to get away from this bottleneck. So let's do that. Let's say we use the Java SE, Java EE concurrency utilities, use executor services, essentially effectively threads, and wrap each of these methods in their own executor service. All right? I'll let you take a look at this code in a second. Okay, it shouldn't look too bad. It's just a asynchronous version of the code that we had before. right? Not too bad. Okay, get assets separate thread, get liability separate thread, calculate query store on a separate thread, wait for F1 and F2, okay, both of those asynchronous results to complete before you do that, and so on and so on. What's the problem here? It's in the code comments. Premature blocking, okay? So in fact, we are still not using maximal use of CPU here because we could be executing the health score path and the credit score path entirely independently. But we cannot do that here because of the premature F1 and F2 blocking calls. Those are two blocking calls that you can't get around. Okay, those are going to block, and then after they are done, only then can you proceed further. Okay, with getting the health score, and you didn't really need to do that. All right, and the answer here is that you could get away from this. You could make this code entirely non-blocking by rewriting it using callbacks. Okay, and callbacks actually do not block. They don't have a blocking problem. However, callbacks have a separate problem. They're called a problem called callback hell. JavaScript developers know this problem quite well. All right? I won't actually go through this code. You can take a look at the slide deck and take a look at my code examples on GitHub, and you'll quickly understand why rewriting this code in callbacks is not a very good idea. So do we have a solution, a sensible solution that avoids callback hell? And the answer, of course, is yes. All right? So the answer is completable futures. All right? Completable futures look very much like the futures we know and love. All right? In fact, they extend Java util future. The big difference, though, is that there is no future.get call. Instead of calling future.get, what you do is that you register a callback. So notice this code down below. You're calling process payment. You're getting a completable future with the type return back. Okay? You're not blocking by calling future.get. What you're calling then is then accept and registering a callback. What you're saying is that when process payment is done, okay, please execute this lambda expression. So this code here, down here, is actually not blocking. That's a key differentiator. All right? Looking at the code above, what's going on? Well, you create a completable future. You immediately return it. Okay? You immediately return it, and the client registers their callback right away. And then you go about doing your business, okay, in another separate thread. And when you are done on this thread, you execute a callback called future.complete. And when you invoke that, okay, any registered callback then will be executed on that separate thread, on that separate execution thread. And hence, as a result, all of this is non-blocking. All right? That is the big magic here. And we could, in fact, rewrite all of our code instead of using Java util future or callbacks, using the Computable Future API. And I'll let you take a look at this code for a second. But let me explain what is going on in the negative 2 minutes that I have. I'm already past 2 minutes. What is happening here is that, number one, the Computable Future, all of these Computable Future invocations, each of them, then combine async, then supply async, then apply async. All of these are registering callbacks. They are non-blocking calls. Beyond that, they are also composable, okay? Which means that you can take one completable future and take another completable future and then say that these two completable futures are related to each other in some way. Okay? A simple example would be execute this completable future after this one is done. All right? And they're also functional. All right? All of these can handle lambdas. As you can see, each of these are actually lambda expressions. All right? So take a look at this code for a second as well. All right? You'll understand it a bit more. You don't have to understand it completely now. You can revisit this code from my slide deck later. Yes, sir. These are, in fact, promises. Yeah. All right. Okay. Moving forward, there's more we can do. The last reactive frontier, the biggest one that we have left in Java EE, is the database layer. And the reason for this is that is not because of JPA, actually. It's because of JDBC. The JDBC API under the hood is actually a synchronous blocking API. All right. So what we need is an asynchronous version of JDBC. Once we have that, we can have JPA APIs that look like this. All right. That instead of returning your list of countries, we can return a completable future of the countries. Similarly, in the UI layer, when we now have an MVC framework in addition to JSF, it looks very much like servlet and JAX-RS. As a result, they can use the same syntax for achieving NIO and asynchronous processing as well. JSF, unfortunately, is tough. Okay, JSF, conceptually, it's difficult to make that an asynchronous reactive API because of the high-level programming model that's there in JSF. However, maybe we could do some things behind the scenes in JSF. For example, we could take example of that Reactive Streams feature that we talked about. And of course, other ideas. Okay, so we're continually keeping our eyes open and seeing what else we can garner in terms of lessons from the reactive programming concepts out there. All right. So that's that. I won't talk too much about it because I'm actually out of time, and I actually want to introduce a few friends. These are all the resources that are there. You can take a look at those later as well. Okay, but let me just finish off by having a little bit of open Q&A and also telling you where the slide deck is. Okay, this is a full version of the slide deck. It is not truncated at all. The full talk actually takes about 90 minutes. All right, so double the amount of time that I have now. But there's a URL for it. Hopefully, it's relatively straightforward. All right. With that, let me take a little bit of Q&A in the remaining time that we have. No? We're all good? OK. Don't go away yet. Don't go away yet. Don't go away yet. OK, so I have a few friends to introduce. Please, guys, come on stage. Okay, so you all know Patrick Curran. I think Patrick will say a few words after he'll sort of finish up this little segment of our talk, of our extended talk. Let me introduce who these guys are. Believe it or not, Patrick gave a talk in the beginning of the conference, the opening talk, and he said he talked about adaptive JSR and the like. Well, guess what? Here in Bulgaria, you actually are already doing all of that. Okay, the Bulgaria JUG is already part of a member of the JCP. All right, and they actually already participate in several adaptive JSR programs. In fact, I would say these guys are probably one of the most active adaptive JSR participants that we have. So I'll.
Actually, it's not only us, it's all of us. It's not only us three, it's all of us.
All of us, yes, all of you, in fact. So with that being said, I'm going to let Patrick comment on the work that these guys are doing. I'm also going to first let these guys comment on the stuff that they are doing.
Okay, so I hope all of you have heard about the Bulgarian Java user group, right? So if you haven't heard, we are here for some 8 years from the Sun times, and we are here in internet, juk.bg, and we do every month, we do free seminars, hackathons. In the summer, we do code retreats. We do some other cool stuff, so follow us here. We have free beer at our seminars. Everything is free. Free as in a beer. So, yeah.
Okay.
Okay, very fast. This is the site. We don't use Facebook because Facebook deleted our group. If you search for without explanation, if you search for Google group BG you will actually the first hit is a mailing list for a Google group. I hope that all of you know how a mailing list is used, but you can join. It's free, and you will receive everything at your email. And also, if you open the Java community process website, basically there is in the recent members there is a Bulgarian Juk over there, so it's something official. And there was a question yesterday about the Sofia user group, or there was an idea of Plovdiv user group like 6 years ago. I just have to say is that the Bulgarian community is not that big. So that's why we don't have so many user groups. We are not the London user group or something like that. And we decided, okay, we will have one big group, a Bulgarian user group. It's even not called Java user group Bulgaria, it is a Bulgarian user group. So even for people that are not living in Bulgaria but are Bulgarians, everyone can be and is a part of the group. You just have to join and come to our events and submit a talk and have fun and do some hacking on the...
So Ivan, do you want to say a few words about what you're doing with Adaptive JSR in particular these days? That work is very, very important.
Very quickly, we try to contribute 2 patches in OpenJDK. We are adopting OpenJDK here, running some hackathons with Jigsaw. We also did MVC 1.0 hackathon, as well as here, as in our group a month ago. And we will continue doing adopted JSR hackathons in our JUC.
So what this means is that these guys are actually changing the very language that you are going to be working on from 2 to 3 years from now. They're actually affecting change in Java SE, they're affecting change in OpenJDK, and they're affecting change in Java EE APIs. Okay? Think about that for a second.
Okay, we really are out of time, so I just want to say thank you to you guys for participating and to encourage the rest of you, if you are not already attending some of these guys' events, you should do so. Java is what it is, not because it comes down from above, but because everybody helps to create it, and that includes you. I encourage you to do so. Thank you.
I also thank you.
Thank you.